Oh, hello there! Back for more information about filters? Let's take a break from passive components though. Let's talk about this chip. Oh, right, you cannot see it. Let's do some magic then. I wasn't told much about this chip. Our master engineer Luca gave me this note and told me to try and figure out what it does. Just in case it's a famous chip, I won't cheat by trying to read what it's called. Supply voltages were obviously selected to work with Red Pitaya's supply connectors. So let's hook it up. I will connect two output probes to each of the chip's inputs and the first input probe to chip's output. I'll leave alligator clips floating since I won't be working with high frequencies. Also, all probes are in ×1 mode. This way, I should be able to set inputs through Red Pitaya and observe what happens. Now, let's take a look at the screen. I will set the first output to be a DC output at 0 volts. And the second one to be a sine wave. Output is jumping between plus and minus 1 volt, which would suggest that I'm hitting Red Pitaya's limits. Let me set the input probe to ×10 mode and in hardware as well. Aha! So the signal was exceeding Red Pitaya's default 1 volt limits, and now one is at minus 2.5 volts and the other at 3.9 volts. This behavior would suggest that this chip is either a comparator or an operational amplifier. Comparators aren't at all that useful in analog circuits, so I will go on a limb and say that this must be an operational amplifier. Luca said my deduction was correct. This is an operational amplifier, OpAmp. This one is OP37 to be exact. We chose it because it's a part of this learning educational kit that the Red Pitaya team recommends to learn about electronics. Let's see how it works. Let's start with basics. OpAmps need supply voltage to work. It is normally positive on the plus node and negative on the minus, but sometimes it is connected to the ground instead. When talking about OpAmps, we usually ignore supply voltage and just assume that it is sufficient. Now let's draw OpAmps symbol. It is a triangle with two inputs, one inverting and the other one non-inverting, and one output. When powered on, OpAmp will try its darnest to make sure that the voltage difference between its inputs will be 0. With no way to influence input voltages, output will hit saturation voltage whenever inputs aren't exactly the same. In this mode, it acts as a comparator, where output hits positive saturation when positive input is greater than the negative, and vice versa. What would happen if I connected output to the inverting input and signal generator to the non-inverting one? Let's connect the input probes to observe the signal generator and OpAmps output. As it turns out, OpAmp doesn't hit saturation straight away. It just amplifies the difference between plus and minus inputs with an amplification factor. When voltage difference is high enough, output will hit saturation, but when voltage difference is small, output will be linearly proportional. In this wiring, OpAmp adjusts output to be exactly the same as input. Such a circuit is known as voltage follower. How about this? Positive input is connected to ground. Signal generator is connected to potentiometer's first pin. Middle one is connected to negative input and the remaining pin is connected to OpAmps output. What will happen now? The first thing that will pop into your eye is that the output signal is inverted. The second thing that you should notice is that the signal's amplitude is different. It can be greater or smaller, depending on what position the potentiometer is in. At one point, the signal gets clipped because it exceeds OpAmps' output range. Let's talk about the clipping first. This OpAmps range is a few volts lesser than its supply voltage. There are some OpAmps that are called rail-to-rail, which means that their output range equals their supply voltage. In any case, the output of an operational amplifier cannot exceed its output range. What might bother you is why output is inverted and amplified or dampened depending on potentiometer's setting. Looking at a schematic, I will connect both inputs with a dashed line. This reminds me that OpAmp will try to make those two voltages the same, in this case 0 volts. In calculation, I will assume that OpAmp has successfully equalized the voltages. Here comes an equation. Or, if we express output as a function of input voltage, minus explains the inversion and the fraction explains amplification or dampening. This circuit is known as an inverting amplifier. But we aren't done yet. Let's find out how we make a non-inverting amplifier without stacking two inverting amplifiers in series. That would be unnecessary and expensive. I will now swap positions of ground and signal generator like so. Want to see what happens? No more inverting, just like I wanted. But observe this. If I turn the potentiometer one way, the signal soon gets clipped, just like before. But no matter how far I turn the knob in the other direction, the signal never gets attenuated below the original's amplitude. The lowest it can go is to the same as the input signal. This is easy to explain if we take a look at the schematic. Those two resistors represent the potentiometer. At one extreme, this one is 0 ohms, and the circuit is actually just a voltage follower with an extra 10 kilo ohm resistor, which doesn't do much. Output voltage is calculated in the same way as before. Both inputs are connected with a dashed line to remind us that they are both at the same voltage, which is input voltage in this case. So here we go. This one is simple to flip around and express output voltage as a function of input. With that written down, it becomes very obvious that the signal can't be attenuated. The nature of the circuit has given it the name non-inverting amplifier. This video is full of simplifications to keep it short. However, all of those exact calculations are used even in bigger projects. The things that I left out are reserved for ultra-advanced circuits and university exams. Now that we have learned about operational amplifiers, we will use them in more advanced circuits. And now a challenge. What if you wanted to make an operational amplifier with a gain less than 1? There is more than one solution. How many can you find? Let us know in the comments below. In the meantime, like, share and subscribe. Bye!